Utilization. Modern automation relies heavily on controllers, which are reshaping a wide range of industries. They have altered the way systems work with their enhanced control, intelligent decision making, adaptability, and connectivity. Controllers are opening the door for more utility, better performance, and sustainable methods by utilizing innovative algorithms and connectivity. Like many devices, controllers are not an all in one implement, but an assembly of different parts. Some of the most significant parts are, and we'll start with processor and memory. A controller's memory and central processing unit, or CPU, are its brains. The system's control tasks are carried out by the processor, which is frequently a microcontroller or microprocessor. In order to assess the sensor data, make decisions, and generate the right control signals for the actuators, it carries out a series of computations and algorithms. Program instructions, variables, and temporary data needed during operation are stored in the memory component, which includes both read only memory or ROM and random access memory or RAM. While RAM serves as a temporary storage for data and variables during runtime, the firmware or software that defines the controller's behavior and functionalities is stored in ROM. Together, the processor and memory enable real-time processing, effective data management, and the execution of control algorithms, resulting in precise and timely system control. Input-output or I/O interface. The most important link between the controller and the outside world is through the input-output interface. It makes it possible for numerous sensors, actuators, and peripheral devices to exchange data and signals with the controller. The I/O interface allows the controller to receive sensor input from other devices such as temperature sensors, pressure transducers, or position encoders, which offer essential data about the state of the system at any given time. In order to regulate and operate the system, it also enables the controller to send output signals to actuators such as motors or valves. Analog to digital converters. By converting analog signals to digital data that the controller can process and manipulate, analog to digital converters or ADCs are essential components of controllers. Real world measurements from sensors such as temperature, pressure, or voltage are captured and converted into discrete digital values using an ADC. During this conversion, the analog signal is quantized into a string of digital numbers and sampled at regular intervals. The controller's microprocessor or microcontroller can subsequently process the generated digital data to carry out various computations, implement control algorithms, and regulate the system for the desired outcome. ADCs enable precise measurement and control by providing accurate and quantifiable representations of analog signals, ensuring that the controller can effectively monitor the system's behavior and respond accordingly. Communication interfaces. Digital controllers' communication interfaces act as the entry point for communicating with other systems and devices outside of the controller. These interfaces provide for seamless connectivity and efficient communication between the controller and other components, including sensors, actuators, supervisory control systems, human-machine interfaces, and even other controllers. The term communication interface refers to a range of protocols and technologies, including modern networking techniques like Ethernet or wireless connections, as well as serial communication standards like UART or SPI or I2C. Controllers can transmit and receive data, commands, and status updates using these interfaces, enabling real time coordination, control, and monitoring. Communication interfaces also enable remote access, configuration, and diagnostics, enhancing the flexibility and usability of controllers. Through the years, the invaluable practicality of controllers had these devices operating at every corner of our lives. No matter the environment, you are most likely to find at least one controller operating in it. Whether it's an industrial production line or a simple washing machine, these devices are being automated by controllers to decrease human intervention and increase productivity. However, these devices differ a lot as each environment they are used in. So, when it comes to environments, we'll start with residential. Various applications of controllers are used in residential settings. One significant application is in home automation systems, where their integration with the smart devices allows for centralized control of various systems, including lighting, HVAC, security, and other systems. Through smartphones or other connected devices, homeowners can remotely access and modify these systems, providing convenience and customization. For this type of system to be implemented, the controller must be connected to all devices it automates and compatible with them, whether it's other controllers or a switch for lighting in a room. For a long time, this has been done through wires, but in recent years, new technologies emerged, and most of these connections can be operated wirelessly. Although very useful, these systems come with their drawbacks as they increase the vulnerability to cyber attacks, especially if the system is connected to the internet. Controllers are also heavily used in home appliances such as refrigerators, ovens, washing machines, and dishwashers. However, these controllers are designed for single purpose uses only and are not versatile for programming and reuse in other applications. For example, a refrigerator controller enables a precise temperature control, automated defrosting cycles, and notifications for maintenance or door open alerts, but it can be switched for a microwave oven's controller unless it's programmed by the manufacturer, and even so, you are most likely to run into compatibility issues. In commercial environments, controllers are crucial because they offer automation, regulation, and optimization for a variety of applications. BASs or building automation systems, for example, integrate various subsystems such as HVAC, lighting, access control, security, and energy management. In order to make these systems operate properly and conveniently, controllers serve as the central brain coordinating and regulating them. In order to optimize energy consumption and maintain ideal working conditions, they continuously monitor temperature, humidity, occupancy, and other environmental data. Additionally, controllers are also utilized in fire protection systems as they collect data from detectors and sensors to initiate appropriate actions in case of a fire emergency. They have the ability to sound alarms, start sprinkler systems, manage ventilation, and contact emergency services. Commercial settings gain from immediate detection, quick action, and efficient fire suppression. Furthermore, controllers offer advanced features like remote monitoring, system diagnostics, and fault detection that allow for preventive maintenance and guarantee the dependability of the system. In commercial environments, controllers are also used for power management, especially in large buildings. These systems look very similar to industrial power management systems as they mostly use PLCs to manage power sources and other switching and monitoring functions. to evaluate power demand, voltage levels, and energy usage trends. Controllers examine real time data from energy meters, sensors, and smart devices, and with this information, processes can be implemented to reduce peak demand, manage load balancing, and optimize power factor correction by incorporating controllers into power management systems. Commercial environments can efficiently monitor, regulate, and optimize their energy use, which results in lower energy costs, increased sustainability, and higher overall power efficiency. Industrial environments. Controllers offer precise control and monitoring capabilities for a variety of industrial applications, enabling smooth operation, increased production, and greater safety. In industrial settings, controllers are the computational centers of process automation. PLCs are frequently used to operate and monitor production lines, machinery, and complex industrial processes. These controllers receive data from sensors and other devices as inputs, process it, and then carry out control operations according to their programming. Controllers improve processes, minimize human error, and boost production by automating functions including machine operation, material handling, and assembly processes. They make it possible to precisely control parameters like speed, temperature, pressure, and flow rate, assuring a process's consistency and efficiency. Another prominent application for controllers in industrial environments is the VFD, or variable frequency drive. VFDs, also referred to as adjustable frequency drives or inverters, control the frequency and voltage of the electricity that is provided to electric motors to control their speed and torque. These devices controllers can be programmed by technical personnel, and their output is in the form of manipulated sinusoidal waves, which powers electric motors. Depending on the VFD, the inputs might vary from switches that determine its method of operation to analog sensors that change the frequency and voltage according to their measurements. Furthermore, these devices can be operated via communication by other controllers such as PLCs. VFDs also discard the need for mechanical control mechanisms like throttling valves or dampers by altering the motor's speed to fit the actual load needs. This improves process control, reduces equipment wear and tear, and saves a lot of energy. Moreover, controllers are also used in electricity generation and distribution as they monitor parameters such as voltage, current, and power quality, ensuring the electricity is delivered with acceptable limits. Load balancing, power factor correction, and precise protection are all executed by these devices as well as real time monitoring. Methods of operation. Various methods are used by controllers, from straightforward open loop control to intricate closed loop control involving proportional, integral, and derivative actions. With the use of these techniques, controllers are able to maintain set points, regulate systems, and react to changing circumstances. So we have open loop, closed loop, proportional control, integral control, derivative control, and PID control. And we will be going in detail into each one of them. Open loop. The simplest type of control is open loop control, in which a controller doesn't receive feedback. The controller in this case provides control signals depending on a predetermined set point or series of actions, without taking into account the actual system response. The controller makes the assumption that the output will follow the anticipated trajectory. Systems with predictable and repeatable processes, where accuracy and precision are not essential, are good candidates for open loop control. Timing of traffic signals, irrigation systems, and typical timer-based processes are a few examples. Closed loop. The most prevalent and widely used way of operation for controllers is closed loop control, sometimes referred to as feedback control. Closed loop control uses feedback sensors to continually check the system output and compare it to the intended set point. The controller modifies the control signal in response to the system output signal to move the system output closer to the target value. Compared to open loop control, closed loop control offers more precision, stability, and responsiveness. It's widely used in process control, robotics, HVAC, and industrial automation applications. Proportional control. Another commonly used method is proportional control, where the controller output is directly proportional to the error signal. The error signal is the difference between the set point and the system output measurement. I'll say it again because this is really important. The error signal is the difference between the set point and the system output measurement. The proportional gain, which modifies the controller's reaction time and sensitivity, is multiplied by the error to determine the control action. Reduced steady state error and quicker system responsiveness are two benefits of proportional control, as it does not take into account the rate of change of the error. Using it alone might result in overshoot or undershoot of the target set point. A proportional controller's output is high when the error is high and is lowered as the error decreases until the system output measurement reaches the specified set point, then the output is zero. However, this method doesn't take into consideration that even if the controller's output is zero, the system output might still increase, causing an overshoot. In that case, the controller will attempt to lower the system output to reach the set point again in the same manner, causing an undershoot and so on until the system stabilizes. Depending on the system, if the proportional gain is tuned right, the system output will oscillate for a period of time and then stabilize. Nonetheless, if the gain is too high, the system output may never stabilize and will oscillate indefinitely. So, in simpler terms, what proportional control really does is that it lowers the system output when the error is lowered. As we've explained before, the error signal is the difference between the set point and the system output measurement. So when the system output measurement gets closer and closer to the set point, the error will be decreasing. And so the system output will be decreasing because the system output equals the gain times the error. Now, this works great on paper. However, it's not that good in the physical world. Take a temperature controller, for example, that is connected to a heater and a sensor. And we select the number X as our set point. As the controller grants power to the heater, it will be heating up. And the temperature will start to rise until it reaches X. Now, when it reaches X, the controller will disconnect power from the heater. However, the heater will remain hot, basically, for a period of time. And this might cause an overshoot. This is why tuning this controller is really important. However, in other control methods, we can solve this issue and we will see how when we explain them. Integral control. Integral control, sometimes referred to as integral action or reset control, complements proportional control by factoring in the accumulated error over time. The integral term in the control algorithm calculates the integral of the error, and this accumulated value is used to adjust the control signal. Integral control gradually reduces any persistent error between the system output and the desired setpoint by continuously summing the error and consequently increasing or decreasing the output gain. Integral control reduces steady state errors and improves the controller's capacity to precisely track the setpoint. It assists in addressing biases and disturbances in the system, but if improperly adjusted, may cause oscillations and a slower reaction time. So we can comfortably say that integral control is a more complex version of proportional control. Actually, integral control has proportional control in it. As you can see in the picture in the slide, the KP term stands for proportional and the KI term stands for integral. And integral control in some cases is also called PI control, with the P standing for proportional and the I standing for integral. So what does integral control really do? Integral control introduces time into the equation. So unlike in proportional control, the controller is no longer, in proportional control, the controller is responding to the value of the error. But in integral control, it is also reacting to the value of the error over time. Meaning, even if the value of the error is consistent, the system output will continue to increase as long as the value of the error isn't decreasing. Derivative control. The rate of change of the error signal is the main focus of derivative control, which is a crucial part of control systems. By analyzing how quickly the error is changing over time, it aims to predict how the system will behave in the future. The control algorithm's derivative term calculates the error's derivative and uses the results to adjust the control signal. The derivative action can be included into the control system to provide stability and dampening, lowering overshoot and enhancing reaction times to changes in the error rate. In systems with quick changes or disturbances, derivative control is invaluable. However, as useful as derivative control is, if tuning it poorly can exaggerate noise or generate instability in the system. So, like integral control, derivative control is also a more complex version of proportional control, and it also contains it, hence the KP term in the picture in the slide in front of you. Derivative control is also called PD control in some cases. So, what does derivative control actually do? Derivative control introduces the rate of change of the error into the equation. This means that the system is going to react to how swiftly the error is changing. So if the error is increasing very fast, the system output will be increased. And if the error is increasing slower, the system output will be less than when the error was increasing fast. If the error is decreasing, also the system output will be decreased as fast as the error is decreasing. PID control. The PID control or proportional integral derivative is a prevalent and extremely efficient approach to control systems and processes. It provides an effective process for system control and optimization by combining three control actions: proportional, integral, and derivative. The proportional term provides immediate response. The integral term eliminates steady state errors. And the derivative term improves stability and response to changing conditions. Engineers can tune the PID controller to suit the various dynamics of the system and achieve optimal performance by regulating the gains of each component. PID control is often used in a variety of industries. Its control is used in temperature control systems to maintain a defined temperature set point by regulating heating or cooling inputs, as well as in robotic systems to provide precise and smooth movement by regulating motor positions or velocities, and in HVAC systems as well to keep interior temperatures where they should be. PID control ensures accurate and reliable operation in industrial processes by controlling variables such as pressure, flow rate, or pH level. So, by far, out of all the control methods that we've mentioned, PID control is the best, hands down. PID control sums up the three control methods: the proportional, the integral, and derivative, resulting in a very efficient and precise control method for control systems. It takes all the advantages of the proportional, integral, and derivative methods and compiles them into one. As we've established before, the diversity of controllers is vast and will keep expanding. Nonetheless, some of those controllers have stolen the spotlight from their counterparts due to their substantial practicality and versatility. We will be going into the explanation of these controllers, and we will start with the PLC, or the Programmable Logic Controller. PLCs have revolutionized industrial automation by providing efficient and dependable control solutions for a wide variety of applications. PLCs, which provide precise control, real-time monitoring, and seamless integration with a variety of tools and systems, have emerged as the foundation of industrial operations. Older industrial facilities frequently used manual relay-based control systems, which were mostly replaced by PLCs. Richard Morley invented the first PLCs as an alternative to relay systems since they are complicated and prone to malfunctioning. PLC's potential was quickly recognized by manufacturers, who then started incorporating them into their systems. There are many benefits to using PLCs, and we will start with ease of programming. The programming process typically involves selecting an appropriate programming language, such as ladder logic, function block diagrams, or structured text, and using specialized software to create and debug the program. Understanding the requirements of the control system, sensor inputs, and intended outputs is essential for PLC programming. By customizing automation solutions for particular industrial processes, users may program PLCs to enhance productivity, dependability, and safety. Furthermore, PLC programming provides flexibility, allowing for upgrades and alterations as system requirements change over time, in addition to reusability in other systems as it can be reprogrammed. To program a PLC, you need to do some research on the PLC you're working with. Usually, the manufacturer provides you with the information you need on their web pages or in the manual of the PLC. However, some common things you need are a computer, means of communication, usually an RS-232 or Ethernet cable, PLC software, and the PLC communication drivers, which both are provided by the manufacturer. And from there, you can explore and get familiar with the software and the programming language you're using. Reliability. Withstanding temperature changes, electrical noise, vibrations, and other industrial challenges, these durable devices are particularly made to work in difficult conditions. PLCs have functions like redundancy, fault detection, and self diagnostics to ensure continuous operation and reduce downtime. They undergo extensive testing and research to follow industry standards to guarantee high levels of reliability. PLCs also include backup and restore features, enabling quick system recovery in case of a power failure. Variety. PLCs are available at a variety of price ranges to accommodate the various demands and spending limits of businesses. There are several easily accessible, inexpensive basic PLC models that are particularly popular by small enterprises and startups, in addition to sophisticated and feature rich variants. These basic PLCs provide fundamental features and are created to specifically fulfill the need of less complex automation operations. For organizations who are just getting started or have limited resources but yet need dependable management and monitoring capabilities, they provide an affordable alternative. These reasonably priced PLCs frequently include a condensed list of I/O or input-output choices, fundamental communication protocols, and condensed programming interfaces. Efficiency. The efficiency of PLCs extend to both their ability to regulate systems and how much energy they use. When compared to other control systems, PLCs have comparatively low electrical power consumption since they are built to be power efficient. Additionally, PLC's efficient power use reduces heat production. In control systems, heat dissipation is crucial since too much heat can harm the component's functionality and longevity. Due to PLC's decreased heat generation, complex cooling systems are not as necessary, which further decreases energy consumption and simplifies system design. Monitoring and data acquisition. PLCs provide real time monitoring of crucial parameters and the capture of vital data due to their ability to connect with a wide range of sensors, instruments, and equipment. In monitoring applications, PLCs act as a centralized control hub that enables operators to monitor multiple equipment and processes from a single interface. They enable rapid identification of abnormalities or deviations from ideal operating conditions by displaying real time data, trends, alarms, and warnings. PLCs also provide remote monitoring, allowing users to connect to vital information and keep an eye on operations from any location. Another crucial component of PLCs in industrial applications is data collection. PLCs effectively gather data from a variety of sensors and devices, obtaining useful data on environmental factors, status, and process variables. For process optimization, performance assessment, preventive maintenance, and regulatory compliance, this data can be recorded, saved, and analyzed. PLCs provide a variety of configurable data storage choices such as internal memory, external storage, or integration with more complex systems like SCADA or supervisory control and data acquisition or MES or manufacturing execution systems. Connectivity. The exceptional connection capabilities of PLCs enable easy integration with a variety of devices and systems in industrial automation. PLCs provide a variety of interfaces and communication protocols, facilitating effective data transfer and functional control amongst various components. They can communicate with sensors, actuators, motor drives, human machine interfaces, also known as HMIs, supervisory control and data acquisition systems, or as we mentioned before, they're also called SCADA systems, and enterprise level networks. PLCs offer a variety of connection choices, including Ethernet, Modbus, Profibus, Profinet, DeviceNet, and many others. These protocols provide dependable and quick data interchange, status monitoring, and control command transmission between the PLC and connected devices. Drawbacks of PLCs. PLCs have unquestionably revolutionized industrial automation. They provide a wealth of advantages and make effective control and monitoring of complicated processes possible, as mentioned before. PLCs do, however, have certain drawbacks that should be taken into account, just like any other technology. We'll start with cost. One drawback of PLCs is their initial cost. Some PLCs can be expensive to acquire, especially for startups or small firms with tight resources. The expenses cover the hardware as well as the software, programming, setup, and training. PLCs may require a substantial investment, therefore, it is important to carefully weigh the potential return on investment and long term advantages. Second, we have programming. Another drawback is the complexity of programming. While PLC programming languages such as ladder logic or structured text are designed to be user-friendly, they still require a certain level of expertise and knowledge. Hardware failure. Even though PLC reliability generally is worthwhile, it is not immune to potential faults. PLCs can have hardware issues or software faults just like any other electronic device, which can cause system downtime and production difficulties. To reduce the risk of failure and guarantee the dependability of PLC systems, routine maintenance, software updates, and backup procedures are required. VFDs or variable frequency drives. VFDs are indispensable controllers used in a variety of applications since they provide precise control over motor speed and reduce energy consumption. The power source and the motor are linked together by the VFDs, which provide variable output in terms of frequency and voltage. With this versatility, the motor may run at various speeds to meet the requirements of the application. VFDs are significant as they can deliver precise speed control, energy efficiency, and improved motor performance. A variable frequency drive operates similarly to a speed controller for electric motors. It regulates the motor's electrical power supply, which alters the speed and torque of the motor. Electronic circuits in a VFD transform incoming electrical power into an output with a changeable frequency and voltage, and so the user can adjust the voltage and frequency to control the motor's rotational speed. Benefits of VFDs. Precise motor control. One of the key advantages of VFDs is their ability to provide precise speed control. Unlike fixed speed motors, VFDs allow for adjustable motor speeds, enabling fine-tuning of processes to match specific requirements. This level of control enhances the overall system performance, ensuring optimal operation and productivity. For instance, in manufacturing environments, VFDs enable smooth acceleration and deceleration of conveyor belts, improving material handling efficiency and reducing product damage. Efficiency. Another notable benefit of VFDs is their energy efficiency. VFDs optimize energy usage through adjusting the motor speed in response to demand. When lower speeds might be sufficient in many applications, motors often run at maximum speeds, wasting energy. By lowering motor speed when less power is needed, VFDs minimize this inefficiency and result in significant energy savings. For instance, in HVAC systems, VFDs can adjust the speed of fans and pumps according to the cooling or heating needs, significantly reducing energy consumption and operating costs. Performance and longevity of motors. VFDs minimize sudden starts and stops by controlling the motor's speed and torque, which lessens the mechanical stress and damage on the motor. This leads to reduced maintenance and longer motor life. Furthermore, enhanced motor protection functions provided by VFDs, such as overload protection, voltage control, and thermal monitoring, protect the motor from damages and increases its operating lifespan. Connectivity. The capacity of VFDs to provide complex control functions and integration capabilities is another important advantage. VFDs can communicate with various automation systems, including supervisory control and data acquisition or SCADA systems, programmable logic controllers or PLCs, and human-machine interfaces, also known as HMIs, enabling seamless integration and centralized control. This increases operating efficiency and decreases downtime by allowing operators and engineers to remotely monitor and control motor speeds, access real-time data, and diagnose faults. Ease of use. One of the notable advantages of variable frequency drives is their ease of use and programming, making them accessible even to those with limited technical expertise. Technicians can easily set up and modify motor settings with VFDs due to their user-friendly interfaces and straightforward control panels. VFD programming usually involves basic parameter settings, eliminating the need for complex coding or specialized programming skills. Additionally, many VFDs come with built-in diagnostic tools and troubleshooting features that assist in identifying and resolving issues efficiently. This ease of use and programming empowers operators and technicians to quickly set up, configure, and fine-tune the VFDs to match the specific application requirements, whether it's adjusting speed parameters, configuring control modes, or setting up alarms and fault diagnostics. Drawbacks of VFDs. While variable frequency drives provide many advantages, there are also certain drawbacks to be mindful of. Harmonics. VFDs can introduce harmonic currents into the power supply, which can affect the performance of other electrical equipment connected to the same system. These harmonics can result in voltage distortion, which may lead to complications including overheating, interference with delicate equipment, and reduced power quality. Harmonic filters or line reactors, for example, may be required in addition to other hardware to address this issue, thereby raising the system's overall cost and complexity. Electromagnetic interference or EMI. During operation, VFDs produce electrical noise that may interfere with surrounding electronic equipment and sensitive machines. For instance, the EMI produced by VFDs can interfere with the operation of precision instruments or communication systems, or result in data inaccuracies in industries where these systems or equipment are essential. In order to reduce the risk of EMI and ensure compatibility with VFDs and other sensitive equipment, appropriate shielding and grounding measures are required. Compatibility. Careful motor size and compatibility considerations are also essential for VFDs. When the VFD and motor are not properly matched, problems including motor overheating, decreased efficiency, and shorter lifespan may occur. The torque characteristics and insulation rating of the motor must be accounted for to guarantee compatibility with the output characteristics of the VFD. Inadequate VFD and motor matching can lead to expensive equipment damage and unanticipated downtime. HMI or Human Machine Interface. HMIs have a crucial role in modern industrial automation given that they bridge the gap between operators and machines. It is a graphical user interface that enables operators to communicate with machines and control systems. By giving a visual representation of data and allowing users to monitor and manage various processes, it acts as a link between humans and machines. Touchscreens, buttons, indicators, and other input-output devices are frequently found in HMIs and allow users to set up instructions and get immediate feedback. Programming and using an HMI entails multiple steps to provide effective communication between operators and control systems. Using specialized software, designers define screens, buttons, indicators, alarms, and data displays that correspond with the established specifications to provide an interface that is user-friendly. The program also enables the setting of data exchange with control devices, communication protocols, and visual data representations. Once programmed, the HMI is integrated into the entire control system through a network connection. Benefits of HMI. User-friendly interface. HMIs offer a user-friendly interface that makes it simple for operators to communicate with intricate control systems. Operators can more easily monitor operations, acquire information, and manage equipment thanks to the graphical interfaces, touchscreens, and easy navigation. Real-time data visualization. HMIs feature real-time data display, allowing users to monitor process variables, system parameters, and alerts. Graphs, charts, and color-coded indicators, for example, provide a clear overview of system status and performance. Centralized control. By offering a single interface for controlling several systems and processes, HMIs centralize control functions. Operator efficiency is improved and the need for manual intervention is decreased when they are able to supervise numerous pieces of equipment, change settings, and respond to alerts from one convenient location. Alarm management. HMIs facilitate effective alarm management by providing auditory and visual alerts for unusual system events. Operators can quickly address issues, acknowledge alerts, and take necessary action, reducing downtime and enhancing safety. Data logging and analysis. HMIs often include data logging capabilities, allowing operators to capture and store historical data for analysis and optimization purposes. This data can be used to identify trends, track performance, and make informed decisions for process improvement. Integration with other systems. HMIs may be combined with other systems like SCADA and MES or manufacturing execution systems to exchange data and give a comprehensive overview of the entire process. This integration increases coordination, simplifies data flow, and improves system performance as a whole. Customization and flexibility. HMIs may be customized to meet particular application demands, enabling operators to set up displays, layouts, and functionality according to their requirements. HMIs can also be updated and reprogrammed. Due to its adaptability, it can be reused in different systems and meet future system requirements. Drawbacks of HMIs. Complexity. HMI design and programming can be difficult and time-consuming, requiring skilled professionals. It might be difficult to design user-friendly interfaces and guarantee seamless interaction with control systems, especially for large-scale applications. Reliance on technology. HMIs are highly dependent on technology and are susceptible to system errors, software glitches, or compatibility issues. Operations can be affected by technical problems, which may call for quick troubleshooting to reduce downtime. Cost. HMIs could require costly upfront expenses for hardware, software licenses, installation, and maintenance. Additional costs could be incurred for customization or system integration. Cybersecurity risks. HMIs are potentially vulnerable to cybersecurity risks since they are often connected to networks. System integrity, safety, and privacy could all be compromised by unauthorized access, data breaches, or malware attacks. To reduce these threats, extensive security measures and frequent upgrades are necessary. It is crucial to keep in mind that while these disadvantages do exist, they can often be reduced with suitable design, implementation, and continuous maintenance. The advantages of HMIs are likely to exceed their disadvantages by addressing these issues, making them an essential tool in industrial automation and control systems. Process controllers. Process controllers are digital devices utilized mostly in industrial settings to regulate and control specific process variables. They monitor and adjust parameters like temperature, flow rate, pressure level, pH, and more to maintain a desired set point. These controllers are essential for maintaining optimal operating conditions, ensuring product quality, and improving system efficiency. They find extensive applications in manufacturing, chemical processing, power generation, food and beverage production, water treatment, and oil and gas refining. Examples include temperature controllers in furnaces to maintain consistent product quality, flow controllers in water treatment plants to optimize chemical flow rates, and pressure controllers in HVAC systems for proper airflow and temperature control. Process controllers enable precise and automated control, enhancing productivity and reducing waste in various industries. Benefits of process controllers. Precise control. Process controllers ensure that process variables are maintained at intended set points by providing precise and accurate control over them. This accuracy aids in the process effectiveness, product quality, and overall system efficiency. Flexibility and adaptability. Process controllers provide flexibility in altering control parameters to take into account changing production demands for changing operational circumstances. They are applicable to a variety of industrial environments because they can be quickly modified or programmed to handle various processes. Data acquisition and analysis. Operators can collect and analyze process data using the built-in data logging and analysis features found in many process controllers. To increase overall process efficiency, this data can be used for performance analysis, problem solving, optimization, and decision making. Remote monitoring and control. Process controllers allow for the remote monitoring and management for industrial processes through the integration of modern communication technologies. As a result, operational flexibility is increased and real-time decision-making is made easier, resulting in easy access and management of the process variables from a central control room or through web-based interfaces. Reduced energy consumption. Process controllers help optimize energy usage by maintaining process variables at optimal levels. By adjusting control parameters such as flow rate or temperatures to match the required demand, energy waste is minimized, resulting in reduced energy expenses. Drawbacks of process controllers. Although process controllers provide many benefits, it's crucial to be mindful of potential hindrances. Here are a few limitations regarding process controllers. Complexity. The design, programming, and configuration of process controllers can be complex and requires specialized skills and knowledge. This complexity may result in longer implementation times and the need for experienced personnel for setup and maintenance. Potential failure points. Process controllers rely on electronic components and software, which can at times malfunction or fail. System disruptions can be caused by technical problems, including hardware failures, glitches in software, or compatibility issues, which require for immediate examination and repairs. Maintenance and support. Process controllers might require regular maintenance, updates, and technical support. To avoid system failures and guarantee continuous operation, it is crucial to maintain regular maintenance schedules and the availability of technical expertise.